Okay, I will start now. So only one student is here. So anyway, can you hear me?
Yes, sir. Yeah,
Okay.
I can hear you.
Uh, last week, I will start from what we discussed last week, and another thing is that there was a lecture series, like link each lecture together. So this is the last lecture for that lecture series. So we have another 3 lectures, but those 3 are separate each other. So this is the last lecture the, in the lecture series, so what we discussed until today. So, so before I start today's lessons, I will recap the last previous few lectures what we discussed. So we discuss alternative stress and mean stress together when it's happened together. What is the behavior of the fracture and everything? So sigma m, if it is equal 0, that means if there is 0 mean load, so there is no any mean stresses. Uh,
Excuse me, sir.
yeah,
Sir, I can't see your screen.
I'm sorry. Uh, yeah, can you see now?
Yeah, I was okay.
It is fine, no?
Okay, then.
Okay. So, so I didn't discuss too much things, so I just explained the. But you hear me, no? At the
Yes, sir.
time
Yeah.
you heard me, okay? So mean stress, if it is equal 0, that mean it's like only alternative stress. So we can apply the kf to the ascent curve as a reducing factor. Like in the stress, you can use to kf value to divide the strength. So don't use the I mean, no, don't use, but you can use. But normally the fatigue stress conservation factor will use to ascent curve as a reducing factor, strength reducing factor. But if it is mean, so this is the nature. So we know everything. We discuss about this curve in one lecture, and this one second lecture. This is third one, like that we discuss. This is the thing with the stress conservation factor. If, if only alternative stress available in the on the element, okay. And if mean stresses, if it is not equal 0, that means there is mean stress, then we need to apply the stress intensity factor into the stress. So you need to multiply, so it is increasing factor then. So stress, so you need to introduce the kf into the stress. So that is a very general thing, otherwise it will be very complex, that's why. So this is the if mean stress, if it is equal 0, you can use the fatigue stress conservation factor for the strength calculation. But if it is not equal 0, that means if it is have value, so you need to use fatigue stress conservation factor into the stress, not the strength. So I hope you understand that. So let's see how we can use then if it is equal 0. So that means there is a multiple force acting. So mean stress and alternative stress together, that is the meaning of that. So then you need to determine point of failure in component, like what are the weaker point. So what are the loading points? So you need to identify that point, and out of those point, you need to identify the weakest few points. So you can't find out all the points stress conservation. So so normally you need to find out which one is weakest weakest. So according to the stress you can find out that, then you can calculate the number of cycle or anything. So after finalize the what is the weakest point, like that. So determine the failure uh, point, weakest point, then determine type of magnitude of nominal stresses for each forces. So you need to find out the stress value that as a magnitude, and the direction as well. So each nominal stress. So if you remember last time what we discussed this example, so you if you remember, there is only 3 force available: the W reactions upward, and the side the lateral friction and tangential friction. So, but even though there is 3 load, you can see that there is a 5 type of load. I mean forces apply on the component, the shaft on the shaft. Then we can categorize to each load value to the different category, 2 category. If it is mean load, you can account it as a mean load. If it is alternative load, you need to account that alternative. Then you need to find out. So first you need to identify what are the loads available on the component. Then multiply each nominal stress by appropriate Kf. So in here you need to find out if it is a bending. So you need to find out the Kf value for bending. So if it is a torsion, you need to find out the Kf value for the torsion. If it is axial, you need to find out the Kf value for axial. So likewise, you need to multiply by that nominal stress by stress consideration factor, fatigue stress consideration factor, according to the loading time. And then you need to categorize each stress value, stresses to relevant category. There is a 2 category, mean stresses and alternative stresses. You need to identify what are the alternative stresses, what are the mean stresses. Then you need to find out the one single value for the mean stress and alternative stress. For that you can use Morse circle theory or the equations. If it is a very simple thing, if the 2 load stress values are perpendicular, you can use Pythagoras rule like that. So combine individual component to produce a single sigma m and single sigma a. So like this. So the Morse circle law, the equation, you can see. Then you can find out the one single alternative stress. This is one single mean stress. So likewise, you need to find out the one single value. Then generate the Goodman diagram using SNN, that means endurance limit and this ultimate stress. This should be SU actually. So you can generate that line, then you can find out where you are. So this is the Goodman line. So we already discussed these things. So this is alternative stress, y-axis. This is x-axis mean stress. So we already discussed these things. And this is the Goodman line. So you need to find out the y-axis limit using endurance limit, x-axis limit you need to find out using ultimate tensile strength. And you can calculate the other values using that. So you need to find out the equation of this curve, and according to that you can find out if it is a shifted to downward, you can find out new equation of curve, or if you are somewhere here, you can find out the factor of safety. So different things you can calculate. It's up to the questions. Yes. So then we discuss the non-linearity of between the stress and loading. So then you can't so at that time also you can't use Kf value to the stress. So I told you need to use to that stress consideration factor, fatigue stress consideration factor, into the load. So you need to if you are going to calculate the factor of safety using stress, that is not correct if it is non-linear. So you can see in here load and stress relationship, it is not linear, it is non-linear. So then you can't use stress to find out the factor of safety. So last week what we discussed, those things we discussed. So you can find out the factor of safety using load value. So up to this point we use stress or load. Each one you can use, but if it is linear only, you can use stress and load. So if it is linear, so something like this, so even though you can use load or stress, you will get the same value for the factor of safety. But if it is non-linear, you can't use stress value to find out the factor of safety. Keep in mind that. So yeah, so if it is non-linear, you need to draw you need to find out this value and you calculate the factor of safety.
Yes, sir.
Yeah.
So in the previous slide,
yeah.
So mean the stress we can't use in the nonlinear format. We can't multiply the stress in KF, right?
So I couldn't get it.
We can't multiply the KF into stress when considering the nonlinear equation, nonlinear graph.
Yeah. So stress means in here it is kind of strength. Okay. So if you use find out the this theory, this nonlinearity theory, we normally we use for the find out the factor of safety. Okay. So
Okay.
if we have nonlinearity between the load and stress between those two, so that means if you increase 1 Newton, if also the stress also if it is increased via the 1 megapascal or 2 megapascal, if it is a linear, so if you increase 2 Newton, if it is a 2 megapascal or any other unit, so same rate, so you can use either stress. So you know what is the factor of safety? Factor of safety is maximum stress divided by stress you are going to apply on that. So maximum allowable stress on the element divided by the stress you are going to apply. So that is the factor of safety. So, but you can't calculate the factor of safety using that stress value because if there is nonlinearity. But you can use for that load value, the maximum load allowed that element, allowed by that element, and apply maximum load. You are going to apply some value, that value as a load.
Okay.
So don't use the stress value if there is an nonlinearity like this. Okay. So if you identify there is a kind of nonlinearity, don't use stress to calculate the factor of safety. That is the meaning of in here. But when you are going to calculate the load value using that equation, like Sn equals CSCL CD times 0.5 SU divided by KF, at that time you can calculate the strength divided by KF. But if you are going to plot the Fn curve or Sn curve, so keep it in mind. So if there is I already mentioned that the two there is a different curve you can plot for the each weakest point. If there is a groove, you can draw the Fn curve, Sn curve or Fn curve for the groove. And if there is a pillar, you can draw the Fn or Sn curve for the pillar as well. And each the curves cross each other. So assume the 10 to the power 3 cycles lowest value give by the groove, and 10 to the power 6 cycle lowest value for the stress given by pillar, something like that. So then you need to consider both 2 points. So we discussed in the tutorial as well this kind of questions. So at that time you are in trouble. So for that you can use load value at that time. So you need to introduce the fatigue stress consideration factor into the stress. So you need to multiply the stress by the fatigue stress consideration factor, and then you can find out the strength without that KF value. If you remember, did you do some exercises? Then did you do that? Some questions?
Yeah.
So if you do, you can recognize what I'm explaining. So then you are going to calculate the stress with the KF, and that value and the strength value without KF should be equal. Then you can find out the maximum load. Like that. The maximum, that 10 to the power 6 cycle load value, and you can calculate the factor of safety at that same different way if there is nonlinearity. You are not using to calculate the stress ratio to calculate the factor of safety if there is nonlinearity. Are we clear? If you don't understand, just tell me. I will explain in the tutorial if you want. What is the point what I explain in here? Did you got what I'm saying?
Can you explain? Yeah, I got. Yeah, I got. But if you can explain the tutorial question, it's better.
Okay, what can I do for you? You can get the that's tutorial what I explained you last time, and so if you do the exercise, so even though I explain in here using different word and different graph and anything you can't understand without doing exercise
Yeah.
yourself. So if you do the
Yeah.
exercise, so you can what you can do. So I will get that tutorial and I will ask what is the point you can't understand. Then I can explain that point. That is better way because I already discussed the tutorial as well. So I already upload the tutorial and the same thing the lecture. The both together I already upload the course web as well. So if you don't remember those theory, what you can do, the download that video and you can listen that the video. So I already explained that one in the
Okay.
lecture number 5 or 4. I don't know. I didn't remember, but I already explained that one. You can listen that. Okay.
Okay.
So I can explain next week if you don't understand that one furthermore.
Okay. Okay, sir. I
Okay.
will ask.
Is it okay?
Is it okay, sir?
Because if
I
I
will go.
explain now furthermore, so if you don't know what I'm explaining, you can't recognize because I can't. That is the one whole lecture. So I can't explain in here within few minutes that one. So I will get okay. I explain this one, and so according to that things I can say like this, like this, like this. So then you need to know what is the thing what I explained last week and or previous few weeks. Okay, but today I will just show you this is the point and something like that. Then if you don't recognize still after I explain at that point also, so what you need to do, you need to refer the last few lectures. So go through that lecture, and at that time, after that video lecture, watching the video also you can't understand, then you can ask. Is it okay?
Okay, sir. Okay. I will ask on the next week.
Okay.
If I
So we discussed this one also. We can calculate the factor of safety using Goodman line. So if there is a linear increment, you can use this line. If it is a sigma m0, sigma a only vary, then you can use the factor of safety, calculate the factor of safety using this line. And if it is only sigma m vary, you can use this line. So if there is any other ratio variations, so you can calculate the different line and find out the factor of safety. And we discussed the surface feature. So when it's a fail after fracture, what is the surface look? So then you can observe the cross sections and you can tell what is the reason for this one. Is it over stressing or is it high stress consideration? You can just how many stress consideration points are there, something like that. You can explain using watching, observing that particular cross sections. So we already discussed this one. So today we are going to discuss the fracture mechanism. So the fracture mechanics. So basically, we will discuss in here a crack growth. So we already know there is due to that crack, there is a stress consideration. So during the stress consideration lecture, we discuss there is a stress razor. All the stress razor we will consider as a crack. So sometime we will make the stress considerations point artificially. Sometime there will be stress consideration point naturally, not naturally, but automatically there will be stress consideration point. But normally groove pillets are this kind of stress considerations points. So we will try to avoid the high stress consideration using smooth groove and smooth pillar, something like that. So if you introduce notch, so that is also artificial crack. So during this lecture, we will discuss, so still we don't know what is the, so only we know the stress during the stress conservation lecture, the circular shape, circular, the hole, around the circular holes, what is the stress variation and other thing you can calculate during the stress conservation laboratory also you will discuss that. Am I right? So you all of you now complete the lab 1. At that time also you use the circular shape small hole through the plate. So at that, around that hole you will calculate the stress conservation. So if you change the whole shape like ellipse, so we already know the AB ratio, that there, if there is ellipse, so there is a two diameters, principal two diameters, not only one single diameter for the circle, but the ellipse not only one single, there is a two principal diameters. So if you get as A and B, so according to AB ratio, that we can change the ellipse shape. So we discussed that one also in the stress conservation lecture. So that's only the shape, that are the only shape we have to we only discuss until today. So we will consider during this lecture. So how, according to the different shape of the crack and the crack geometry, it's according to crack geometry and the crack uh, initiations and crack growth. So those details we will discuss in this lesson. So again, you will feel sometime it is a repetition, but it is not a repetition, it is extended. Okay, so where we stop in this stress conservation, so it is this part is extended part from that point. So due to stress conservation, so you know the endurance limit without stress conservation, this is the equation, Sn equals Cl Cd Csn. So this is the non-ideal specimen without stress conservation. That means stress ratio. Without stress ratio, this is the endurance limit. So this one or this one, this is expand of Sn dash, Sn prime. So no stress consideration here. But if you introduce stress consideration, we will introduce Kf. So dividing this part by Kf. So but you don't have any idea, just you will calculate the Kf as a stress conservation around the stress razor, but you will get some particular one constant value for the Kf. So you don't have any idea about quantitatively that stress consideration. Just you have this one single value, you don't know how it's vary. So that variations and how to uh, grow that crack and how to initiate that crack, all those things quantitatively we will describe during this lecture. So the theory behind this one, we will only consider linear region in here. So that theory we call linear elastic fracture mechanism. Okay. So we will discuss only linear region. You know what is the meaning of linear region? Elastic region. Okay, not, we are not going to plastic region. So in elastic region only we will deal. So the elastic regions fracture mechanisms theory. There is a specific theory. So those theory we will use to quantitatively analyze the crack growth. So I think you understand what I mean. With the Kf value, you don't know what is the behavior of crack. Just you know what is some one single value. So rather than using that one single value, if you can furthermore explain the crack growth behavior, that is very good way to the quantitative explanation. Okay. So you can see in here initial crack length A naught. So in here just explain how to vary with the fatigue stress with the crack length. Okay, so consider three identical specimen, so same size and same crack length, initial crack length. each pre-crack to crack length of A naught, that is initial crack length, and then subject to fatigue stress S1, S2, S3. That S1 is larger one, S3 is the smallest one, as shown below. So you can see here. So when you apply the so this is the fatigue stress. So this is the fracture point. So if you apply the S1 fatigue stress, so this is cycle. Okay. This is only alternative stress. There is no any mean stress. If there is mean stress, this particular alternative stress will be shifted upward or downward. So if it is a tension, it will be upward. If it is a compression, it will be downward, something like that. So you can see the x-axis applied cycles, number of cycles. The y-axis is crack length. So how crack length vary with the number of cycle, you can see. So they are not going to change the amplitude of this cycle. Okay, so same magnitude they will apply, but with the time you can see. So with the time means number of cycles, it will take some time. So that time. So according to the number of cycle or with the time, you can see the crack length, that A value. This A naught is initial value. It will propagate. So you can see the crack length propagation with the S1. S1 is highest stress one. Okay, highest stress. So S2 is middle one. S3 is the lowest one. You can see it will take long time. It will take long time to get the fracture. So this is the fracture point. So, and it will propagate more and more. So this is the fracture point. You can see this is cross line. So cross point. So with the assume this is 100 and this is 150, this is 200, something like that, just for an understand. So if it is 100, within 100 cycle, this is get as A1 and this is A2, A3. So you can see A1 is smaller than A2, A2 also is smaller than A3. So number of cycles also higher, but you can see crack length with this stress, it can survive until higher crack length. So that's mean effective cross section, even though reduce when it's propagate here. So the crack propagation mean this crack will penetrate to the other side. So with the time, with the number of cycle, so this crack will be propagate to this direction, because this is tension. This crack will open. So high stress somewhere here. So the crack will open like this and it will propagate to and penetrate to the other side. So with the time, with the number of cycles, so this will propagate, and effective cross-sectional area at the initial point, this is the effective cross-section area, but it will reduce with the time. So you can see with the lower stress, it can survive. Even though it's a low cross-sectional area, it can survive. That is the meaning here. So A3 is higher one, so it will break in somewhere here, but A2 is somewhere here, A1 is somewhere here, so it will break very quickly. Without propagating too much, it will break. With the higher stress, it cannot withstand much longer. That's the meaning of that. And it will, with the shorter crack length, it can break. So that is the meaning of this graph. I hope you understand that. So that means the crack length also reflects the stress, and you can, if you know the stress cycle, so you can, if you know the crack length, you can find out the fracture point. So crack length, initial crack length is govern the crack growth rate. Okay, and yeah, I already explained crack propagation rate larger than the fatigue life is shorter, and these are the factors. Hence, it can be shown the total life failure is depend on initial crack length, that is A naught, and the stress magnitude. So with this, you can see the magnitude, if it is vary, the crack length also vary and fracture point also vary. So stress magnitude and the final fracture resistance. So those are the main three factors govern the total fatigue life. So if you remember what is the meaning of total fatigue life and the growth fatigue life, so you will understand what I'm meaning here, because we discussed this one in the lecture number 3, I think, during the fatigue testing. So we can do the fatigue test using Murray test. At that time we discussed this thing. So, there is a different type of specimen. So there's basically two categories. So particular one type of specimen we can use to calculate the total fatigue life, and there is another type of category you can calculate the crack growth only. So the initial crack length and stress magnitude and the final fracture resistance, those things will govern the total fatigue life. So I just remind the last few lectures. Okay, so at that time we discussed what is the main difference total fatigue life and growth fatigue life. Growth fatigue data and total fatigue data. So yeah, how can this information be used to predict fatigue life and for the design of component expected to fail under fatigue? So that is a question. The format more useful for design is plot for crack growth rate. So in here we are not going to, so with this graph we cannot predict something, just we can get some idea. Okay, with the magnitude, the number of cycles to fail, it will be changed, and crack length also will be varied, something like that data we can get. But we can't get much more details from here. For that we can use another curve. So that curve has a we can plot crack growth rate versus stress intensity factor. So that is a new term you will learn during this lecture later. I mean, so don't confuse with this stress intensity factor and fatigue stress conservation factor. So fatigue stress conservation factor and stress intensity factors are both things, two different things. Okay, so not the same thing. So fatigue stress conservation is Kf, but stress intensity factor normally we will call the K. Or normally if it is a range, it is delta K. Okay. So I hope you understand what is the difference between the Kf and this K value. This is not the, again I will repeat, this is not the fatigue stress conservation factor. This is different term in here. We call it is stress intensity factor. So we will plot the curve. The y-axis is delta K, and crack growth rate, it is dA by dN. That is this is the differentiation. So with number of cycles, we can, with respect to number of cycles, you can differentiate the crack length. So this is x-axis. So you can plot the curve. With that curve, you can predict the something. Okay, so rather than here. So already it's proved. Okay, so that's the thing. So this is the curve. So you can see. Okay, so in here they get the log delta K. So I'm sorry, in here they consider the delta K is y-axis, x-axis. Okay, so delta K is stress intensity factor. Again, it is not a fatigue stress conservation factor. Okay, stress intensity factor, it is x-axis, and dA by dN, that is differentiate part. So you can get the as a y-axis. So you can get the curve like this. So you can see there's a delta KH, KTH, that is the threshold value. So even though you increase the stress, so until this point it will not crack will not growth. You can see that this is dA by dN. So until this point, that crack length, it is as a constant. So if it is vary with the number of cycle, then only you have value. That is a differentiate mean. So differentiations give some value. Only a has a function with the n. So a is, if it is constant, it will not vary. So then you can see dA by dN will vary. And one time there's three region you can see. So the second region, it has a linear portion. The third region, it has a again non-linear region. So this first region, there is a until some point. So delta k should be enhanced until this point. Then only the crack will be propagated. So it will something like that. So if you apply the 10 kilonewton, so that will crack will not propagate. That means that 10 kilonewton is not enough to exceed this delta k th. That means threshold value should be passed by that 10 kilonewton. So if you apply 20 kilonewton, so if it is enough, more than enough to equal this value, then it is the point to start the beginning the crack growth. Then if you apply the 21 kilonewton, or more than one single decimal point, more than 20 kilonewton, it will try to propagate. So it has a threshold. So the first region, so we call it has a non-continuum behavior. So it will this region is governed by the microstructure of the material. So you know the shaft, if it is shaft, it the atoms arranged in the different manner. So it has a microstructure. So that microstructure will govern these regions. Okay. So this behavior, this line shape and other things. And then mean stress. So not the alternative stress, the mean stress. And environment. Environment is the temperature, pressure and other things. So environment. So this region 1 will govern by those factors. Again, it is large influence. So there is a small influence will be different other things, but the large influence will be highly impacted by these three factors. The region 2 we will call as a continuum behavior. It has a continuum behavior. So the large influence will due to the environment, certain combination of environment, and mean stress and frequency. Frequency means we can call it a number of cycle. Okay. So within 1 second, number of cycle increase mean it is the frequency. So frequency and mean stress, and small influence by microstructure depending on the material. So it's depending on the material actually microstructure. So in here microstructure is a governed significant thing. In here it is small, but the mean stress and the environment again the large influence. So third region, so it is static mode behavior. So large influence by microstructure. You can see the all three regions governed by the microstructure, but the second region microstructure is not governed by small the large factor. Okay. And mean stress, thickness of the component. The environment will not influence too much. There's a little. So you can see in this diagram, the region 2 again it is linear. So you can get the equation for this region. Second region, it is kind of y equals mx time, mx plus c time. But you can't get the one single equation for the curve. So scientists already derived the equation for the curve for the second region. So this equation valid for this region. So you can see the equation dA by dN equals C delta K times M. The power delta K power of m. So you can see this is kind of y equals mx n power. Okay. So it is not y equals mx then. So this is already proved. This is the equation of this curve. So the third region, even though this is the dotted line explain the prediction line. We will predict it will be something like that, but actually it will happen like this. So that equation should be follow. If it is followed by the third region, it should be like this, but it is not. It will be deviate from somewhere here. You can see. So at this point, the final fraction. That is the meaning of that. So critical fracture will be happening here. So this is the curve behavior. You can see we will normally consider the second region, this region. So this is the equation. So you can see in here, this is the I couldn't tell you. This is normally we will cause this is kind of S shape. You can see this is like S letter of S alphabet S shape. So we call S curve. That's a S shape. So this is the actual data for the titanium alloy. You can see the actual data. So it has the same feature like this. First region, second region, third region. You can see in here. So when the delta K decreasing and constant load amplitude test. So in here, load is constant and delta K will be decreasing to this side. So you can see the variation of the crack growth rate and stress intensity factor. So you don't want to keep in mind this unit and other things. So you can easily derive that unit because dA by dN. So normally length will be measured by meter. The number of cycles per cycle mean dN means per cycle. This the rate, that's the mean of rate. Okay, meter per cycle, and this is a megapascals square root m. So you can see this unit in the questions. You don't worry about the unit. Keep in mind the unit and other things. So we will derive the equation for delta K later. Okay, so I told you we will define the delta K, what is the meaning of delta K and what is the equation for delta K later, but this is the curve we will use to calculate the crack growth data. Okay, so yeah, as I told you that it has a shape curve independent of initial crack length. The quantity delta K takes into account the crack length and the stress range. Okay, so initial crack length we will not account in here. Okay, so even though initial crack length is much higher, then it will happen. But if it is crack length is lower than this point, so we don't want to worry about that. So initial crack length independent of initial crack length. So S curve is independent on the crack length and initial crack length, not the crack length, initial crack length, that A naught. The quantity delta K takes into account to crack length and the stress range. So we are going to derive the equation for that delta K now. So delta K is a function of crack length, not the initial crack length and stress range. So stress range is the magnitude of the stress. So let's see if the stress intensity factor is correctly chosen for the given component and the crack geometry, then integration of the S-shaped curve can provide the fatigue crack growth life. That means if you find out the area under this curve, it is the crack growth life. So life for the component subject to different stress level and different initial crack size. So this is the equations for the curve. So we call this curve Paris equation. Okay, the person who find out this equation is a Paris. So this equation calls the Paris equations. So this is come up with this linear region. Okay, so this is the represent. For example, the linear portion for the dA by dN was delta K curve can be described the Paris equation form of the form. This is the equation. So C and M are constant, as I told you. So in here, M doesn't mean the gradient. Okay, so normally C will be intercepts and M will be gradient. So don't be mess up with that meaning. So keep it in mind. In here, C and M are constant, not the gradient and intercept. Okay. So
Excuse me, sir.
yeah,
This equation
yeah.
is only valid for the third region, right? Not for the second region. It's only
But,
valid for the third region. It's
no, linear
static mode.
portion. Linear portion. You can see.
A linear portion.
Third region is not a linear. You can see. It is non-linear.
Okay, okay.
So you think like that because it is mentioned in here. That's why.
Yeah.
Isn't it?
Yeah.
But you can see this is the extension of the second region. So they predict it should be like this, but it will not. I told you. It will deflect to, actually it will deflect.
Yes.
So this is the prediction line. So prediction line only valid for the second region, you can see. So if it is prediction line more extended to the other side, you can see it should be like this, but it will not. It will deflect somewhere here. So it is valid for only second region. So we are normally deal with the second region. Okay. Are we clear? Hello, are we clear? Did you understand?
Yes.
Okay. So in here, C and M is not the normal intersectional gradient. Okay. But so in here you can see that M means slope and C means intersection. But you can't find out that C and M using that particular graph. Okay. So don't think that you can extend that curve for the get the intersection and the gradient and like that. So that is not the thing. But the slope and intersection will be the different material already tabulate. Okay. So if you want to find out the slope of the theoretic perlite steel, so that M value 3 is given. Again, so I told you it is not the gradient and distribution. So what you are thinking, okay? So normally you will think if you draw the curve, it is y equals mx plus c. That c and that m is, and this m and this is different, okay? So but they call this is slope. So normally if you think slope should be somewhere here, no, m and c sub should be like this, but it is not the same thing in not that the mathematical relationship with the y equals mx plus c, and this one is different. Okay, this is like a y equals some constant plus xm. Okay, so this is the actually this is not the linear also. This is this equation only valid for the linear region, but this equation not the linear, not the linear. You can see this is power of x has some power. Okay, power value. So you can see here the different slope have different distribution have. Okay, so normally you can use these data in the questions. If they provide M and C like this manner, you can find out the proper what is the material. So they will provide, assume this is 75 T6 watt aluminum. So you need to get those values. If they didn't provide that exactly what are the value, and if they only provide this table, you need to find out using that table as well. And yeah, the stress intensity factor, it is the function of stress range. So that is the thing here. So in your A levels, you already this kind of thing. So if we have the something like Okay, function f, this is function. If it is vary with the x and y, so you can get the x and y and some power. This is a and b, and you can find out the constant value and a, b values, and you will derive the equation. Like this in here also, you can see it is a function of stress range and track length. So they already find out the power. So this stress range, it is power a equals 1, and the y something like a, so it has a power half, b equals half, and the constant value the square root 5, something like that. So they already find out. This is the relationship between the stress range and track length with the stress intensity. But you will learn later, this equation also will be vary with the crack shape and other things. Okay? So keep it, sometime if you keep it mind this equation, that sometimes good, but they will provide this equation as well, but it's better if you have rough idea about this equation. So if this one is delta k, this part, if it is equal to delta k, you can introduce that delta k into our Paris equation. So what is the Paris equation? That is dA by dN equals C delta k times that power of, so the delta k you can substitute in here like this. Then, so normally we are not going to find out the crack growth rate. So this is denoted the crack growth rate, delta A divided by dA divided by dN. So that is the crack growth rate. But we are not going to find out. If they ask, you need to find out the crack growth rate, you need to use this one. But normally they will ask number of cycles, something like that. So then what you need to do, you need to subject that particular thing. So if you assume constant absolute loading, that delta sigma, it will be constant. Okay, but if it is not constant, you can use that manner as well. But if it is a constant, then you can use dn one side and da to other side. And if this is constant, what happens when you differentiate with respect to dA, so sorry, integrate with respect to dA, the delta sigma you can take out. It is if it is constant, and 5 square root 5 times m, that power m, you can take it out. So likewise, only remaining part is square root a power m integrate by dA. So all the constant you can take out. So if the sigma, the delta sigma, if it is not constant, you need to find out that delta sigma as a function of a. So that means if cross section vary with the stress, you need to find out the relationship between the cross sections, and the track length will change the cross section, effective cross section. So that effective cross sections and the stress variation should relationship you should know. Then you can substitute as a the stress as a function of a. Then you can again differentiate, integrate with respect to dA. So if you differentiate with respect to dA, you will get the so you need to differentiate with respect to number of cycle in this side, and then you will get the answer for the number of cycle, another thing. So this is the integration. After integration, you will get the, so in here only integration one. If you integrate one no constant value from the n, you will get the same. If you differentiate 1 by dx, so don't differentiate, integrate with 1 by dx, so you will get the x. So this is n, and this side I told you, if it is a constant you can take it out, if it is a constant take it out, constant take it out. And you need to differentiate integrate with respect to dA, with respect to A star to AN. That means the initial we consider in here there is initial crack. So if there is no crack, the A star will be equal 0. If it has a value, you can substitute in here, and that end to the end. That means sometimes the component width, it is a cross section, or diameter, something like that. So n, and so if you want to some particular length, so if you want to calculate the crack length until middle of the cross sections, so you need to calculate, you need to substitute in here, if it is the circular cross section, d by 2. That means half of the diameter, and you can calculate the number of cycles to grow the crack until that point. So I hope you understand that. So you can, how you can use that equation. Yeah. So you can find out we can generate curve of n, even if delta sigma is some other value, and then initial crack size is different. Okay. Yeah. Definitely. So if there is different function, the initial crack size is different. Yes. So if you have any question until this point, you can raise your voice and you can ask any question. Do you have any questions? So there is only 2 participants. Do you have any questions?
No, sir.
Okay. I heard some voice. Do you have any questions? Okay. Yeah, combined fatigue crack growth data in the linear portion, that is regions 2, I told you, of dA by dN was delta K curve for wide variety of steel with the yield stress, yield strength or yield stress, varying from 250 to 2070 megapascal, found to fall into main groups for periodic perlite and martensite steel. So in here, you can see that even though it's like feel like it's a very simple, it's very very subjective. It depend on the material as well, yeah, and it will vary with the within high range. Okay. So you can see with this two graph, the actual data, it doesn't have particular one curve, one line. So it has a band. It doesn't have one single line for the curve. So you can see in here. So even though we only discuss the fatigue test, we have the band for the fatigue data. So then we will calculate the lower band and upper band, then average band, and out of these three we will consider the lower band. So it will reach to the endurance limit very quickly. That's what. Likewise in here also data band is, you can see. So those data value, the first one and second one for the different two material. So the first one for the perlite, and the right side one is a martensite steel. So I think you know what is the main difference in the perlite and martensite. So martensite and perlite is both are steel, but the only difference is the microstructure. So at the very beginning, I told you the microstructure also govern. So I mean it will influence highly to this data. So if microstructure change, even though you see if it is steel, if it is microstructure change, this curve will be changed. So let's see how it can be changed. Okay, you can see in here this graph. You can see the y-axis. The y-axis is value around 10 to the power minus 6. This is 10 to the power minus 4. So this is start from the, in here, assume the 10 to the power minus 7 or something like that. So this range, the data range, it's around, okay, you can get the range 10 to the power 6 to 10 to the power 4. That means it is around 100. Okay, so if you get the ratio, it is around 2.5 factor. If you get the as a factor, this range is varied the 2.5. But in here you can see 10 to the power minus 10 to the power 3. It is factor 4. So this is 2.5 points increase. This is 4 times. So you can see. So how much varied the data variations you can see with the micro structure as well. So you can see the same type of graph, but the data, but you can see the variations. These are not same scale, different two scale. You can see even the same. You can see it's like similar size, but it's different scale in y-axis. So this is 4 times difference. Okay, so the data will be very 10,000. In here 100 times. Within 100, this is 10,000. Range is 10,000. This is 100 to the 150, something like that. So we have bound band. So we will normally, so we will get these kind of data. So normally we will get the linear region like this. Okay, so we will select the band. You can see. So whole material you will get the data point one particular band. Okay, so you can see in here and here. So if you got the selected band, so this all the material has the data point between these 2 points, but you can see different material. This is martensite, so you can see the band, the linear band. The peritic perlite, you have different band. This is austenitic steel, so you can see the different line in here. So this is general scatter band, and the different material has a different band again inside this band. So this is the kind of actual data and variation of the stress intensity factor with the crack growth rate. So you have a rough idea about that. And crack size, for a given crack size, there is a critical value for stress intensity factor Kc. So we call it a Kc, critical stress intensity factor. So in the particular questions during the exam or somewhere, so if they ask, you need to calculate the critical stress intensity factor, you need to find the Kc value. So what is the meaning of Kc? When exceed the results, the crack propagating at the very high speed, the catastrophic failure will happen. So critical value means so it is the point for the crack equations. If I will provide the equation, I will explain it. So already we can state that for a given stress loading, there exists critical crack size above which component will fail catastrophically. So if you remember that threshold value, so if it is reached that threshold value, so that is the point it will initiate the crack growth. Okay, so it is type of critical point. Okay, so I am explaining somewhere here, this point. If I go back somewhere here, this is very critical point. Until this point, crack will not propagate. After this point, it will start to propagate. Note that the stress required to catastrophic failure crack component will be lower than the required fail uncracked component. Example, yield stress and yield strength and ultimate tensile strength. This is considered effect of the crack. So if it is assume that Kc values, that Kc values, if it is when you introduce the Kc and find out the strength, if it is higher than yield point, or normally we will consider the yield point, but if it is ultimate tensile strength higher than value, so that is catastrophically fail. So according to that, you need to find the KC. So when we deal with the question, you will easily understand that. So this is the thing what I told you. We will introduce the distress intensity, that equation with the stress intensity factor. There is another things govern the stress intensity. So that terms we will call Y. So that is the geometry of the crack. Okay, terms of the geometry. So we already discussed this part. Delta K equals delta sigma times square root phi A. So we already know that. So if you multiply by Y, that is a crack geometry terms. Okay, so it is govern the crack geometry. So if it is change the crack geometry and crack size, so stress intensity will be changed. So the Y will depend on the loading type. The loading type is the bending and other things, and specimen size. So if specimen has a higher width with the small crack length, it has a different effect rather than small with the same size of crack. So higher width has a small effect, but large effect will be for the small width. So the crack geometry and specimen geometry and loading type and situation. So the Y depend on these three categories, you can see. So the Y has a function, different function. So you need to calculate the Y separately and substitute in here. So if you have delta K like this, you need to introduce to that Paris equation, that K delta K, and you can again find out the number of cycle to that particular crack length. So you can use that equation this way. Okay. The same equation, only Y terms in here. So Y, that crack geometry terms, we can explain like this way. Okay, so you can see in here finite width plate. So finite width, there is a finite width, and you can see the crack, the initial crack length 2A. So it is in internal crack. So you can see if we increase this width size, the crack length effect will be different. So in here you can see the different three persons, the Pedersen and Sida and Irwin. So those three persons give the three models for the 2A divided by W. That means the ratio between this length and this length. The crack length divided by the width. I told you the crack length even though same, the width when we change, that ratio will be changed. And even though width is same, the 2A, that crack length can change. The crack length, if it is very small, the ratio will be very small. So you can see. So in this 2A maximum value, it will take as a W. That means penetrate to this side to this side. So that's why 2A divided by W, if it is equal 1, that is the meaning of crack. This particular plate separate to two parts, and if it is 0, there is no crack. 2A if it is equal 0, no crack, and here to here, the crack length will be increased. In here W is constant, and then y-axis, so it is in here you can see Ki means the stress intensity. I means intensity, stress intensity. So this equation, stress is the Ki. So these terms, they will take it to this side. So you can see that y value. So that y value, the three models they provide, you can see. So the Pedersen's one, it is something like this, and Sida has different way. So it will not reach to 1, even though the ratio is 1, if it is not reached to 4, this maximum value. So this is the variation. So This is center crack plate. So this is kind of modeling, okay, so with the simulation and some practical data they will use and find out some models to predict something. So the just you can get the rough idea with the crack. So with this model you can get rough idea. So when you change the crack length, that y value variations, even though these three metal has a different curves, so all three curves give the same meaning. So when you increase the crack length, the y value initially not change with the large rate, but when it reach to the w value del d 2a, if it reach to the w, close to the w, that means the effective cross section area when it reduce, that y value highly change, significantly vary, that meaning high rate change. So that is the meaning you can take from this model. So y value will change. So this is two lectures. I will continually do that one. Okay, so the 13 they will consider the two lectures. So they stop somewhere here. So I will not going to recap this one. Okay, so this is we already discussed now. So with this example we can do. So we discuss until this point. They will discuss the until this point as a one lecture. And this part will discuss. They will discuss in the next day. So I will just same day. So this is the example. With this example, you will understand how we can deal with this equation, Paris equation and other equations. So I will read the questions and I will explain and listen carefully. A transverse crack extend 6 millimeter inward from the surface of a 320 millimeter diameter steel tie rod of an extrusion press. Okay, the press load is approximately 2,000 tons, and it's equally shared by 4 such rods. Okay, there is a 4 rod like this. So the diameter this one, and it will carry the this much of load. Okay, but equally share. Okay, so this load will be equally shared, means it will be 500 tons for each row, something like that. Between press cycles, which occur 1,500 times per month, okay, they provide the press cycles as well. There is no load on the tie rods. The fracture mechanism evaluation yields a shape factor. Okay, so they provide the shape factor. Y value they provide. Normally, if they didn't provide, you need to find out y value, but they already provide the y value. You don't worry about the y value now. So you don't worry about the crack size, crack shape and geometry of this specimen. Other things you don't worry. So y already provide, and the equation already provide for the stress intensity delta K, and is assumed to be independent of crack length A. So the independent crack length, the A, the stress and other things. Okay. So then they provide for the more details. The evaluations conclude that when the crack is 75 millimeter deep, the tie rod will be in danger of brittle fracture. So when crack length it is 75 millimeter, it is kind of critical situation. The fatigue behavior of the steel is known from experience to be, okay, they provide the C and M, you can see this is C, this is M, and the Paris equation. Paris equation C and M values they provide, two constant they provide. I told you they will provide the units, you don't worry about it. It is desirable to keep the press operating. How long it will be possible to put off replacing the tie? Okay, you need to find out the number of cycle. With the number of cycle, They provide the per month number of cycle, so you can find out the number of months you can use that particular tie rod, and when you're going to replace it. So you need to find out the number of cycle of this system. Okay, so how we can deal with this one? So you have this equation they provide already by and C and M, so you can use this equation, but don't substitute to the sigma delta sigma like this in this equation. You can separately calculate it. So how we can calculate the stress range? Stress range, it is as I told you, they provide it is in ton. You need to calculate in uh, Newton. So when you calculate Newton, it's a ton. When you convert to the kilogram, it is multiplied by 10 to the power 3, and you should multiply by 9.81 is a gravitation. So acceleration. So you can multiply that one. You will get the Newton value. So then you need to divide by cross section. So you already have the diameter. So this is the radius. So it is circular shape cross section. So pi r square. So you will get the stress because this is a P upon A, load divided by area. It's axial load. So if I draw in here something like this, assume just for understanding, okay, this is kind of rod, 4 rod like this other side. So this is carry the 2000 ton. Okay, so this is axial load. So when you're going to find out the stress for the axial load, P divided by A, load divided by A. But in here, if you need to calculate for the stress for one rod. So even though there is a P load, this value, you need to divide by 4. That is because there is a 4 rod. So each rod, they already mentioned, each rod carries the equal load. They are going to share. So that's why 1 upon 4 here. So you can calculate the stress range now for the particular type. And then you can substitute in here y value they provide, C and M they provide. So this equation you can rearrange like this. So if they provide this equation, you need to rearrange like this. So then n value, so we need to number of cycle to 75 millimeter. So then this equation, so we already discussed how we can rearrange this one. This equation rearrange, then substitute. Okay, in here the integration also they show with the symbols. So if you don't want, you don't show it, but substitute C value y. This is stress range. This is 5, and this is M value, and the start and end you can see. They provide it initially in here. 75 millimeter. There is a 70 millimeter deep, and you can see transverse crack extent 6 millimeter inward. So initial crackling they provide. So initial crackling they provide. So that is the start. So in millimeter, they provide in millimeter. You need to convert the meter. So it is 0.006, and this is the N1. This is not actually N, but this is the critical length. They provide 75 millimeter. So this is 0.075, and this is the integration of the A. So this is kind of, if we have A to the power half, so when you integrate, it is 1 minus half, so 1 plus half, A to the power 1 plus half divided by 1 plus half. In here, it is in minus, okay, because it is 1 upon A times something, A to the power something. So when you get to upward that one, so then it is minus. So when you integrate this one, so I think you know how to integrate, so I don't go to extent. So you can integrate this one. So you should know how to integrate, okay, otherwise you're in trouble. So integrate it and substitute. M value you need to substitute here, and you need to substitute leave it later. So then you will get the keep it mind, you need to substitute stress range in megapascal, okay, in this equation. That is the main important thing you need to keep it mind. You need to substitute in here in megapascal. So you already find out in megapascal, you can substitute in megapascal. You don't want to substitute 10 to the power 6 in here. So ignore the 10 to the power 6, just in megapascal you can substitute. And then simplify that one. And yeah, this, then number of cycle you will get like this. So I'm not going to in detail and explain how to differentiate and substitute. So n value you will get, this is the number of cycle to grow the crack until 75 millimeter. So that is the critical point. So the maximum time to fail you can find out using the given data, because you already know what is the number of cycle to fail. So you know within 1 month how many number of cycles they operate. So if you divide that particular calculate value for given value, so you will get the number of month to fail. So 9.39 means the per number of days. So it is around less than 15 days. 15 days means 0.5 day, 0.5 months. So it is around 10 days, I think it's 10 or 11 days. So 9 months, 11 days, something like that. Note that in practice, we could obviously want to use suitable safety margin. So we can't use until 9.9 months and 11 days. So we need to replace within 8.5 months. So that is a safe margin. Not let the component be used until the point of catastrophic failure. So you can't use until 9 months and 10 days. 11 days you are going to replace. It is not good. So you need to put the safety margin. So before fail the exam, so you predict this will fail within 9 months. So then you need to replace that one before 2 weeks, complete to the 9 months. So that's the normal safety margin. That's kind of normal safety margin you should keep. So that's how we can deal with this kind of equation and this kind of questions. I hope it's clear. And then we need to discuss the crack growth with the different type of loading condition. Okay? And basically there is 3 modes. The crack growth vary with the 3 modes. Not the 3 mode, but we can categorize these 3 modes. The first mode is opening mode. So you can see in here crack will open. So when we apply the tensile load like this, crack will be open. So crack can easily grow. So we call our open mode or mode 1. And mode 2, it is sliding. You can see there's even though there's a crack, this lower part will pull and this will push. So this is sliding. The interface will be slide. Those 2 plates interface will be slide each other. And mode we call it a sliding mode or mode 2. And mode 3, it is tearing. So you know when you tear the paper, you will tear like this. You will bend upper side to inside and this other side, so opposite side you will bend this, so it will tear. So mode 3 or tearing mode. So these are the 3 principal modes we can categorize all these crack propagation method. So normally even though there is a 3 mode, we only discuss only mode 1 in this lesson. Okay, so you have in the syllabus only mode 1, concern the only mode 1, that means open mode, opening mode. So we are not going to discuss the sliding mode and tearing mode, just only opening mode. You can see the crack can easily propagate to this side. So normally opening mode will happen with the tensile load. You already know that. The derivation of the stress field at the crack tip is so crack tip means, I think you know, somewhere here. Okay, equals crack tip somewhere here. It is a high stress concentration point. So the stress field you can calculate using some function. So that function called IV stress function. So the derive that IV. So around this crack point, tip point, stress you can calculate using some mathematical theories. So that theory we can call Fourier transformations theory and differential equations. So using that one, you can calculate the and D operators. So if you know those theories, so if you learn in the mathematics those theory, you can calculate the stress function around this crack tip. So I'm not going to explain the calculation here like we already when we discuss some equation I'm normally will explain the derivation part, but this derivation is a bit longer and you should know the mathematical theory very thoroughly, otherwise you can't easily derive this equation. But if you know those Fourier transformation and D operators and the differential equation very well, you can easily calculate, I mean not too much is, but you can derive this equation. I will just guide it, but I'm not going to derive that equation in here. So that after finding that equation, we call that stress function is IV stress function, the person who find out that one. Yeah, so which is beyond the scope of this course. That's why. So the function calculations we are not going to do in this lesson, but we will use that equation sometime. Okay. So you can see in here the infinite plate, each side y and x side the directions infinite, and crack center crack you can see crack in two-way. And if you want to find the stress at any point, so there is a meaning of here. So if you change the angle, so you can get the any point, and if you any point around this circle, and if you change the radius, you can get the any point of on this plate stress around this crack. So you can use this theory as well. This is sigma y, sigma x, and tau xy. So using this theory, you can consider, you can calculate the stress at any point with the function of r and theta. Okay. So with the radius and theta, that stress will vary. That is the meaning of that. So in here only biaxial stresses. So you know there is no shear stress. But when you are going to calculate the inside things, there can be shear stress, even though there is a biaxial only. So this is general term. That's why they mention in here. So we will use this kind of model to calculate IV function. Okay, that's a thing. So then, yeah, the elastic stress field, the following boundary condition. So if you know the Fourier transformation and differential equations theories, so we should have some boundary conditions to find out some constant values. So those are the value in here we are using to boundary as a boundary condition. You can see at y equals 0, that is the y direction this one. So y equals 0 somewhere in center. The sigma y it is equal 0 because there is no stress. This is free, the material free. If it is cracked, there is no material inside this crack. So sigma y equals 0. Okay. That is one of boundary condition. And at x equals minus o plus infinite, that means this side or this side, in here you can get as sigma x or sigma y. Okay, so this is sigma x, then sigma s that is equal infinite stress. It is our conditions. Okay, boundary, another boundary condition. And in here the x can be lower than minus an, higher than A as well, because this cannot be 0. You can see. Sorry, lower than A. So in here it should be this side. So it cannot be 0 because it will be can only be from here to here, and here to here. I'm sorry, the x yeah, x minus A to A means this side to this side. Okay, this length x they consider as a s. Okay, this length. Okay, in here to here. Okay, whatever. X at x equals minus A to plus A, that is crack tip. Yeah, we consider crack tip. Sigma y, it is infinite. In here, the sigma y means in here. I think sigma x, so it should be sigma x. Sigma x should be infinite because we are going to apply sigma infinite in here. It cannot be changed in here as well. So sigma y, it is infinite. Okay, somewhere here. Crack tip around it is infinite stress. Are we clear? Yes. So those are the boundary conditions, some of the boundary conditions. So then this is ID stress function. Okay. So these functions normally we will derive using differential equation. Okay. This crack growth data rate has a differential equation function. So differential equation function. So differential equation we can solve, and we can derive this kind of equation using Fourier transformations theory and other things. So I'm not going to in detail provide that one. So these functions, so in D operator and other things, you can get this kind of equation. So this is yeah.
So in the previous slide,
Yeah.
Can you explain the theta is increasing, right?
In here there is no theta, the terms explaining. Just they want to explain here with the theta and r. You can find out at any point stress and any stresses. Okay, that's the meaning of that. So in here there is no any theta. You can see in the boundary condition they will not consider the theta. In here all the things, in here theta equals 90, in here theta equals 0. Yeah.
Okay.
So x direction means theta equals 0, no? Y direction means theta is 90. 5 upon 2. Yeah. That's right. Is it clear?
Yeah. So the
yeah.
So plus A and minus A. The plus A is in the right side.
Yeah, this one. Minus A means this one. So because we consider the direction is a vector, so this distance is vector. So we consider the origin is somewhere here, center point. So this side plus, this side negative, minus.
So then where's the crack tip? Crack
tip somewhere here. This is crack. This is crack center. So if we draw like this, so this is the flat crack, no? So if you draw like this circular shape crack, this is crack center. So in here, if it is elongated like this crack, this is crack tip. In the circular shape, there is no crack tip. Okay. So each and every point is a crack tip. But if you have this ellipse kind of crack, these are the crack tips. Are we clear? These two are crack tips. Okay. So then this is ID stress function. So now don't ask again how we can derive this function, because for this you need to do so many calculations. If you know, did you ever do the potential well equation derive? I don't think so. So electron inside the well or something like that. No, you're not. So did you find out the energy band theory? Never ever. Did you heard that? Anyone? Can you tell me? Did you know there is a, in your LOD, you know there is a electrons around the nuclei, there is an energy band. So did you ever heard how we can calculate that energy band and the band energy calculations? You didn't know? You didn't, isn't it?
Not sure, sir.
Okay, anyway.
So
Yeah,
is it the Einstein theory or something?
yeah, kind of that, yeah.
I can like barely remember it.
Yeah, that in that equations, when they derive, they will use this kind of Fourier transformation theory and D operators, if you remember. So it's the same kind of theory, okay? Not same calculation, same kind of theory they will use in here also. Okay. So if you know the Fourier transformation theory, you know this is the lecture series, okay? So if I'm going to explain in here, it will be not the advanced materials course, then it's a mathematics course, okay? So this is the function, okay? Just now you need to know, you should believe me, okay? Not know. So, but if you want, you can find out the ebook. There is so many ebook, and just try to find out the iris stress function, and then they will provide each and every step if you want further knowledge. Okay? Now how we can derive the TDC equation, other things. So we solving this equation. So we have the functions. So solving this equation, you can derive the answers like this for the stresses: sigma s, sigma y, and tau xy. This is like if you remember the second lecture we discussed, if you have initial stresses sigma sigma y and tau xy, if you are going to transfer to the that stress to another angle, so we have sigma x1 sigma y1 and tau x1 y1. So we already derived the equations. So this is similar type of equation. So you can find out at any angle x direction. So if I draw here, so if we have this kind of plate, assume there is a crack, so this is crack. If you want this point is stress. So if you know the radius to that point, if you know the angle for the to the x direction, you can calculate the sigma x this point using this equation, sigma y and tau xy at this point using this equation. Okay? That is the meaning of these equations. So that's enough for you now. I mean, used to this equation. So in here, r when it's reached to 0, that means the radius somewhere here on the crack tip, surface of the crack tip, surface of a crack, that stress will be infinite. That is the meaning of that r equals 0. So you can see when r equals 0, this all the functions will be infinite. So I hope you remember that you don't want to keep it mind this equation. Okay, they will provide if they want, if it is want, but you should have idea now what is the meaning of this equation. Right? With this one, you will easily get it. And yeah, the stresses are product of the position relative to crack tip. Now you know that. In here, you already know that. So the stress we can find out at any point. It's a function of r and theta. That means the position of the crack tip, position of the location, the distance from the crack tip. So that is the meaning of r, and the theta also gives that location. Okay. So crack tip. So that is f theta divided by 2 phi r square root. That means this is f theta, kind of f theta. Okay. This is function of theta. Then this is divided by 2 phi r. That's the thing. This one we already know. This is kind of ki, stress intensity factor. This is delta sigma times square root phi a. So yeah, the factor of this function and factor of factor sigma, that ki, which is function of the remote stress and crack length. Yeah, that is that ki describes the magnitude of the elastic stress in the vicinity of the crack tip, on the crack tip, surface of the crack tip. Factor is called the mode 1 stress intensity factor. So at the mode 1, the ki, This is the function. Okay, so you can see there is no delta part now. If you want, you can put, but delta and sigma is not different. You will use one single value as a constant thing. So in that particular case, if it is a stress range is 60, you will substitute the 60 megapascal. That's all. So the mode 1 Ki value equals that is stress intensity factor mode 1. In here, this is not a 1. Okay, this is 1. Stress intensity Ki 1. Okay, that only they put as 1. Mode 1. That is the meaning of mode 1. Stress intensity factor K1 or Ki1 equals sigma times this one. Okay, on the factor. Yeah, so there is so many expression. Then we can use the equations. This solution valid when r is less than a. I mean, this is around crack surface of the crack. Okay, that's one. In the vicinity of crack tip, the total stress field due to two or more different mode or loading system. That means around the crack tip there is assume there is axial load, and there is a bending, and there is a torsion, different type of load. Inside the crack there is free space. You don't worry about the loading type and other things, but at the crack tip if there is so many stresses moved, you need to calculate the stress intensity factors for the each mode. If you remember, we already did this for the K value as well. Kf, when you're going to find out the for bending, you will find out the Kf value for the bending, and Kf value for the axial load, Kf value for the torsion, likewise. So we call this theory superposition principle, superposition theory. That means those values are independent. So Ka value, the Kf value, fatigue stress considered value from bending, it is independent for the torsion. The torsion independent for the other two, like that. So then only you can use this proposition principle. So that means in here stress intensity factor due to torsion, due to axial load, due to bending, each three independent each other. So then only you can so this is kind of assumption, assume like that. So you can use superposition principle. Then superposition principle mean you can calculate the torsional Ki, bending Ki, and axial Ki separately and get the summation. If it is dependent on each other, you can't get the separately calculated and get the summation. It is wrong. But we assume here those three are dependent, then you can calculate separately and get the summation. Okay. So that is the thing they mention in here. There is a two or more different modes. What you need to do, you need to calculate the Ki value for each mode, then get the summation. Okay. So in general term, the Ki does not appear, and hence the 5 half term are not cancelled out. Okay. So that means these terms we can't cancel out. Okay, so we need to keep. So I will give rough idea in here. So this is, if you don't remember, if you can't keep in mind this equation, you can use, this is the way I'll keep in mind this equation. I'm sorry, this line, this is, just forget this line. So what is the circumference of this circle? So if it is a radius a, okay, if it is radius a, radius not diameter a, it is diameter a, 2a, diameter 2a, okay, diameter 2a, then circumference, it is 2 pi r. Okay, so radius, okay, assume this is a, not 2a, then you can easily give it one. So a, then r equals a divided by 2, then it is 5a. So assume this is kind of circumference of the circle. Normal general term we will consider the circle. So this is kind of circumference of the circle. That's all. That's how I will keep it in mind. This is a short method, but if you can't keep it in mind, don't worry. You can keep it as this one, as it is. But I will keep it in mind. This is circumference. Then 5 times sigma times square root 5. That's the way I will keep it in mind. Okay. Now, so we know we already discussed the geometry of the crack. It's influence the stress intensity factor. But in here you can see the F terms. That means F function of W ratio. A divided by W ratio is the function. There is a function of A divided by W ratio. So this is kind of Y. We already discussed Y. So this is the different way we can explain the Y. So if in the questions, if they provide this kind of way, you don't want to calculate again Y. This is the Y. So you can calculate this value. So normally they will, in the questions, we can easily understand with the example. I will explain. So you can get the idea how we can use this kind of thing. So this is kind of crack length, this is kind of width. So if you remember, when you can find out the Y value, we will always consider this kind of ratio. I show you the graph as well. There are different kind of persons explain the model as well with this ratio. So this is kind of Y. You don't worry about too much. So this is kind of this function they will provide. So what is the relationship between the ratio and this function? Okay? So they will provide a function separately. So then what you need to do, you need to substitute to this AW ratio. So normally they will consider whole as AW ratio as alpha, or sometimes beta, gamma, whatever thing. So you need to find out the alpha and substitute to that function, and you can find out this function value, the substitute here. That's all. So we will call this is modification factor, whatever. So yeah, as I told you, you can see in here the modification factor if the function of AW ratios that Y you can see and Y have to determine from stress analysis. Most are obtained from the numerical solutions. Numerical solution means you need to do the solve the equations by using some mathematical theories, and you can find out the values for the relevant constant. So this ratio and these values are not two different things. So if they provide Y here and this ratio separately, you need to use that as well. But if they didn't provide Y in this equation, you don't worry about. So you can see, as I told you in here, this is width, this is the 2A, the crack length. So then this is the function. You can see this part, and this is the function of AW. A divided by W, that ratio function. So this is the part belong to them. You can say if they provide like this, you can calculate this part separate and substitute in here. And if they provide like this, they will separately provide that function set like this. You can see, or like this, or like this. Okay. So you can use this equation and find out this value and substitute in here. So, and you can see here, if you have different kind of loading conditions, you can see in here the tensile load, and this is center crack. So location of the crack also very important. So you can see this center crack, this is width. Then so in the question you need to be very careful to identify the location of the crack. So this is center crack. Then you need to use this equation or this equation. So you can find out the so this is for small AW ratio. If it is large, you will use different way. this equation, if it is larger. So you can find out the K value, stress intensity value factor. And if it is tensional load, but if it is a surface crack, you can see location is different. Normally we will get the crack length as A. In center crack, it is called 2A crack length. Normally give us a 2A. So you need to get the A half of this length. But in here, total length you will consider as a crack length. With the diagram, you can easily identify that. That means if you have center crack, you need to get the A. Okay, assume this is 20 millimeter. So you need to get the A as a 10 millimeter. But in the surface crack, if it is a 20, this crack length, if it is 20 millimeter, you need to get as it is 20 millimeter. So you can see here. So then you can calculate the Ki using this equation. So Y is provided here. You can see Yn that F A divided by W ratio, that function, the similar thing. So then in here, two surface crack. You can see this side and this side. So then you can't use this equation. You need to use this equation. Okay, different way. So if it is small AW ratio, you need to use this equation. If it is a larger one, so you need to use this equation. So this equation different rather than here. You can see this Y will be changed with the locations and the number of crack as well. And if it is bending, you can see it is bending. Okay, so you need to calculate this different way. Okay, for the bending. So this is the crack. So if it is like this type of crack with this kind of load, you need to use this kind of equation for the Ki. So even though this is the tension, this is not the applied to the center axis. You can see this is the different pattern, loading pattern. So you need to use this kind of equations, this kind of crack type. You need to use this equation. So this is, if you remember, I told you the crack growth rate. We will calculate using this kind of specimen. So at that time they will use the Ki equation like this. If it is inside pressure, so inside the crack, you can see there's a pressure P. Okay. So then inside pressure is P. The outside there is nothing is here. So but inside crack there's a pressure. As in there's a fill the gas inside the crack. There's a gas fill. So then the pressure apply on the crack surface. Then this is the way you need to find out the Ki. And you can see this is the not homogeneous cross section. The cross section vary. So if you know the crack length and this diagonal diameters of the crack, so you can use this equation to calculate the stress intensity. So likewise, you can use with this example, you can easily grab that knowledge. So you can see there is a 4 type A, B, C, D. Not okay, this is not label, but A, B, C. You can see there is a ABC figures. So the different type of crack locations and crack size. The center crack plate has uniaxial tensile load P equals 500 kilonewton. If the load is given, choose the most appropriate loading condition from the figure below and determine the following. Assume this B means the half of it in here. So the B is depend on the figure. In this diagram, it's half of it, but in this diagram, B means full width. Okay. So likewise, you need to identify that one. So no one going to tell you that. T means thickness, okay, and H is much higher than B. That means this height. This can be assumed as a infinite, sometimes something like that. And you can use this. I told you, so sometimes they will call as alpha. That means HB ratio. This HB ratio. This is H, this height, half of it, half of height, and this ratio. Okay, HB ratio. Normally they will get the different ratio, but you need to look at carefully in the questions and identify what are the things. And HB ratio, if it is higher than 1.5, you need to use this equation. And HB ratio, if it is higher than 2, you need to use this equation. And this is the general equations. So you can see here ABC condition. So for the A diagram, this is the curve. This is B. This is C. Okay. So if it is AB condition, A or B condition, you need to use this equation, find out the stress. This is load divided by cross section. You can see this is the cross section 2B in here. You can see this is B, so the width is 2B times T. This is cross section. But if you are going to calculate the stress using C, so you can't get the 2B, it's a B times T. C. B times T. So P divided by BT, it is the stress. So if you know the load, if you know the cross section area, you can find the stress. So this is valid for the AB figures. This is valid for the C. And these curves are with the AB ratio. That means that crack length and the width ratio. You can find out the F using this graph if you want, or you can use this is the curves function. You can use either this equation as well. No worries. So what is the stress intensity factor Ki for the crack length of A equals 15 millimeter? So the first question is, if it is 15 millimeter, that A value is A value. If it is 15 millimeter, what is the Ki value? So you need to find the first stress range. So this is the value. So you need to substitute the stress load value. Then this is in kilonewton. So you need to convert to Newton and to BT, and you will get the megapascal. Alpha ratio, that AB ratio. I think in here it cannot be HB ratio. This is AB ratio. Okay. So AB ratio alpha, and then AB ratio, that value is very close to the 0.1. Okay, anyway, so 0.083. So if it is approximately equal to approximately figure from case is less than or equal 0.4, that means you can see in the case A, yeah, so after 0.4, it is very close to the 1. If it is deviate from somewhere here, 0.3 and 0.1, somewhere here it will deviate from the 1, but until this point it is 1. Okay, F value will be reached to 1. So they just approximate the value, get dash value, so that equals approximately equal 1. Then that AB ratio in here, not AB ratio, if it is just AB ratio, it should be alpha. This should be alpha. This is wrong. This should be alpha. Alpha, if it is less than or equal 0.5, you can consider the F equals 1. So then Ki, you know the function. This if that function and stress and square root 5. Just substitute that equation, F equals 1 in here, the case A, and SG we already know, stress. Then you can substitute in these values. In here, the 15 millimeter, this is center, so the A they provide as 15, so this is 13, but you need to consider 15, so that's why they consider 15 millimeter. Then you will get the value for the Ki. If you don't remember the unit, what you need to do, you just substitute the unit in here and simplify that unit, then you will get the correct unit. This is megapascal, and this is square root meter. So that is the unit. And what is the stress intensity factor Ki for the crack length if it is equal to 90 millimeter? 90. So then same case, so you can calculate, it will give the same value again, not change. And alpha ratio will be changed. AB ratio, it is 0.5, it is higher than 0.4, then you need to use the equation, or you can use this graph. So calculate the F value. So if it is above 1.5, or sorry, yeah, it is above, this should be alpha. So it is above, say, 1.5, you can use this equation. So you can calculate this equation using this equation F value. Then you substitute here, find out the Ki value. So you can see different Ki values. So in here 20, this is 57, around 58. And then what is the critical? This is third question. What is the critical crack length? In critical crack lengths and normally labeled as a AC. For fracture, if the material is normally they will provide the material. So KIC they provide. This is the critical stress intensity factor, KIC. So in this case, A is not known, therefore AC is not known. So you only know the KIC. So what you need to use this equation, and KIC value you can substitute and you can find out the AC value. So you can't go to substituting these value and find out this value. Now we have the K value, the maximum Ki value. So you can substitute that, and you know the F value for the ratio, given ratio, the same equation. So you can find out the in here it is not a K, okay? So it is F. If you cannot check it, it should be F. If A is less than or equal 0.5, we can use F approximately equal 1, then it should be 1. And SG, this is the value. Then find out the AC, critical crack length, using those values. So this is the critical crack length. So these are the three equations, and then these questions critical, after finding out critical crack length, let us take the value for alpha. Then alpha they will check. So the alpha value with the critical crack length, AC divided by B. So AC this value, the ratio 0.119. That's original assumption. A, if it is less than 0.1 was correct. AC 0.21 meter in here meter. This therefore reasonably accurate. So because if it is if you get the ratio above 0.4, this is not A actually, this should be alpha again. This is wrong. The alpha, that ratio, if it is above 0.4, you are in trouble because you can't use that particular condition there. So you need to use different equation. So in here we can use this equation. So this calculations valid for this condition. So this calculation valid for this condition. This should be alpha. So that's how we can deal. So I will explain what is the superposition principle. So again, superposition principles are in mode 1 case. So if we have different kind of loading condition, assume there is a in here they generalize a PQR load. Okay, so loading system, as in P is bending and Q is torsion and R is axial. So then you need to find out the axial Ki value, bending Ki value, and torsional Ki value, and get the summation. That is the superposition principle. Okay. I already explained that one. So then we can, if you have mode 2 and mode 3 also, we can use that particular theory. But combination of different modes, we cannot use that. You know? So mode 1, that means the opening mode, only opening mode with the bending and torsion and axial, we can use the superposition principle. But opening mode and tearing mode and sliding mode, so for each term combinations we cannot apply the superposition principle. Because assume if we have mood 2 and mood 1 together in one system, we can't apply the superposition principle for mood 1 and mood 2. So that means those are not independent. Those are dependent. Mood 1 and mood 2 are dependent. So we can't apply the superposition principle for the each mood separate and combined together. Only inside one mood you can apply the different loading type, loading conditions, and find out the ki values and get the summation. In the mood 2 only if you have, so you can use that particular superposition principle and find out the k total ki. Likewise, so you can see in here kind of illustrations for the superposition principle. So in here you don't have this is a uncracked sample, no crack. So there is a crack, and if you apply the stress this as a tensile load, so then the crack, there is a reaction, the crack surface to other directions, because this will cancel out when you get the summation. Okay, so this should be equal to this one. So that means inside should be pressurized, something like that. Then only there is a reaction to other side, and then if at that time what we can do, we can separate these two. So in here with this compression stress, this will cancel out, this crack will be cancelled out. It's similar to the uncracked sample, there is no crack. But you can, if you can separate these two now, the crack can, the compression part separate like this. This is the thing what happened in the superposition principle. Okay. So you can see there is a crack and it is under tension, and summation with the same crack without tension, only compression at the crack. So if you get the summation of these two, you will get the this one or this one, this one or this one. This is the equal to the this one or this one. The superposition principle, what we are going to do, if we have axial load, you will calculate the ki value separate. Bending load, you will calculate separately and get the summation. It will equal to the resultant of the total condition. I mean resultant condition. So that is the meaning of the superposition principle. Yeah, this is the thing I was already explained. Yeah, so if you get the ki, this is diagram D, this is diagram E. So if you get the diagram D ki value, E diagrams ki values, then it will be equal to this one, and this there is no any stress intensity factor, so this is equal to 0. So all this summation and this stress intensity should be equal. So then you can get the this one equal to this one minus of this one. So inside, if you remember when I explained the internal pressurized gas, if you put into the crack, so you will get, so stress is P, and that equation equal like this. Okay. So if you remember that equations, so stress equal to, stress is P. So then in the megapascal it is P. Then I will show you that equation. So then you will, yeah, this equation. Okay. So that's the thing. Yeah, you can see in here. So you can find out the K. Fracture toughness with that one. I will read this one and I will explain. Using the equations such as K, that is stress intensity, this equation, we have been able to relate the stress between sigma to the stress intensity factor. Yeah, we can imagine that if sigma is increased to progressively larger value, then eventually maximum value will be reached, sigma maximum. That's obvious. After which the specimen will fail catastrophically. If it is reached to the sigma maximum, it will be catastrophically fail. from examining the previous equations, it is easy to see that the stress intensity factor will also have maximum value, known as the critical stress intensity factor, KIC, of fracture toughness. So we call it fracture toughness. Okay. So sometimes you heard these terms already. So fracture toughness. So critical stress intensity factor. That means in the particular example, if you remember, they provide for some critical alloy. It has a fracture tough, the stress intensity factor critical value, KIC. Then we will substitute that particular equation KIC and find out the A value. If you remember that example. So then the KIC, it is same alternative name is a fracture toughness. Okay, critical stress intensity factor, KIC, is a fracture toughness. So what is a fracture toughness? It is a critical stress intensity factor. Okay? Critical stress intensity factor. So, but you need to substitute here sigma maximum. Okay. So maximum stresses we are going to apply, but and that particular example we are not going to apply the increase the stress. So same stress. So we are going to find out the maximum A value or critical A value we can put on the element. So that's the thing. So fracture toughness and critical stress intensity factor, same thing. Okay. So if you using this equation, this is a constant. So the sigma maximum, which is directly proportional to Kc and inversely proportional to the square root A. If you know the half of crack length and everything. So this is kind of relationship between the maximum stress and KIC and the crack length. So this is the actual data, actual values for the fracture toughness. You can see here. This is KIC value for each material. Separately, you can see another other mechanical properties also mentioned here, Young's modular strength and tensile strength. But this is now we know what is the fracture toughness. Yeah, different another materials in here, only steel, and there is aluminum. So that's a different categorization, but fracture toughness you can see. So normally in the questions, if they provide this kind of table in the annex or somewhere, so if they provide in the equations what is the material, sometimes they will not again mention you need to find out the fracture toughness. So you need to use that particular table and find out the KIC value. And you can use that one for the equation to find out the critical crack length or maximum stress value or something like that. It's depend on the question. Yeah, so the fracture toughness, it is indicate how much energy required to propagate crack within the component. That is a fracture toughness. The toughness is normally because energy. The factors is belong to energy terms. It is belong to energy. So normally material has a toughness. So because the toughness is energy absorbed until the fracture point. Normally in if it is stress strain curve, so it is the area under this curve. So in here also fracture toughness is energy required to propagate the crack within the component. So that is the KIC. Okay. So if they ask to define the fracture toughness KIC, so you can note down like that. Following from this, this is clear to KIC's material property. It is material for definitely. It is governed basically microstructure. I told you. Property which measure toughness with tough material generally having KIC value greater than 20 megapascal. So you can categorize. There is a margin. Okay. So if it is KIC value is above 20 megapascal meter square root meter, so you can categorize a tough material. So in the particular question, if they ask can you suggest this as this material soft material, what you need to do, you need to find out the KIC value and check whether that KIC value is higher than 20 or not. If it is higher than 20, you can call as a tough material. But if it is lower than 20, you can say it's soft material, something like that. So the value of KIC for brittle material may be as low has 1 megapascal. So that means the brittle material. So this is kind of general thing, okay? So you can generalize, but sometimes in some cases can be changed. Special cases, exceptional cases can be there, but generally you can say like that. So the KIC value, if it is lower than 1, it is brittle. Certain ceramics such as magnesium oxide has this kind of value. So I incidentally, arguably the main reasons behind the development of composite material was to increase the fracture toughness of brittle material. I told you this exceptional case. So sometimes brittle material, if it is combined with the ductile material, so even though it is a high portion of brittle part, so with the combination of the brittle part, KIC value can be enhanced. So that is the composite mean. So normally the composite is not a natural thing; it is a artificial thing. So normally the peoples are combined two things, different properties of things together, and get the optimum property with the lightweight and high strength, something like that. So you can combine high strength material with the lightweight material. So then you can get the optimum value for the lightweight with the maximum strength, something like that. So composite material you can make, and that's why I told you this is general case. If it can be changed with the application. So with this example, you can identify the. So you will get this kind of question at the exam sometimes, but you can't get this kind of question separately. This can be combined with the particular case, like the shaft, it has a crack, something like that. Okay, so but you need to separate the thing to belong to this kind of theory in the question, and identify separately all those things and calculate relevant answers, something like that. So you can't get the separately this kind of question. Okay, so, but this is the maximum level you can reach in your level. So in this example, the following long rectangular bar of thickness B equals 20 millimeter. You can see this is with and with okay, this is 20 millimeter. No, can be but thickness. Okay, thickness also thickness in this direction. Okay, I think it is inside to the slide. With B 20 millimeter and width W 100 millimeter. It is made from this steel, and fracture toughness KIC they provide 60 megapascals. So you can see this is tough material, okay, and subject to a load P 250 kilonewton during maintenance. Okay, there is a during maintenance there is a they found out there is 20 millimeter deep crack. Okay, so this 20 millimeter and this thickness is two different thing. Okay, this is is a direction. This is in y direction. Assuming elastic fracture mechanisms, okay, LEFM, is it safe to return the barred service without repair? So there's you need to find out the without repairing it can be reused, or you need to replace it. So what you can do, you need to find out the total K value, and if it is exceed the KIC value, you can't use that. So you need to find out the KIC value for the particular case. So K value, stress intensity value. If that stress intensity, if it is exceed KIC value, you can't use this bar. You need to replace it. But if it is lower than 60 megapascal, you can use it certain number of cycle or certain number of little bit more times. Okay. So that's the way you need to do this calculation. So you need to find out the KIC. But in this case, you can see if you clearly and carefully look at this one. This is 60. They didn't mention in here, but in here 60 millimeter. But this syntax is, if I draw here, This center axis. Yes, this is horizontal. So this is center axis is around 50 millimeter. So this is eccentric load. You can see if it is concentric, you need to apply the load along this axis. So this is little bit deviate from the center axis. So this is the E centric load. Due to this, if you apply the axial load, so there is only one type of load, axial load. But in here, axial load and bending both. Due to this load, there is a bending. This due to this distance. Okay, so you know you can calculate that value. This is 10. So if you know this load, you can find out the bending. So there is a two type of load. You need to find out the bending Ki and axial Ki. Then you need to find out the total Ki, axial load, tensile Ki, and bending. So load is not central, and we don't have Y factor for this geometry and loading. Yes. However, both tension and bending loads are present, and for each of these, we do have Y factor. Yes. Recall that Ki is relative proportional stress. We already know this linearity allows superposition theory as follows. Yeah. So sigma we can easily find out because we know the load. We can divide by area. Area we know because we know thickness. We know the width. So we can find out the cross-sectional area. Then we can find out the stress. Then bending moment. When you're going to find out the bending moment, so because you know the load, this is load value in Newton. This is the distance from center axis. I told you is 10 centimeter. So 10 millimeter. So 10 millimeter you can subtract the 0.06, 0.05 from 0.06. Then you will get the bending moment around the center axis. Then what you can do, superposition principle you can apply, as I told you, Ki for due to tensile load, axial load, and then due to bending load, the Ki value. So then you will get the this is the tensile load. This is eccentric due to eccentric load, Ki value. So you can get this is the Ki from this one, total Ki. This is the separately you can calculate that. So for the tensile component, this part, so you need to find out the proper graph then. Proper figure. Because this is surface crack tensile load. So you can find out the Y value for the. So normally they will provide then in the annex on the equation under the equation they will provide this the figure and the Y factor. Okay. So this is the Y factor. So ratio of AW ratio, they if you know you can find the Y. You know already stress. So in here they eliminate the phi part. So but you need to introduce phi as well. Anyway. So I'm sorry they eliminate the Y. Sorry. Anyways, so you need to check that equation, okay, Ki equation for the relevant graph. Sometimes there is no phi. Let me check. Sometimes there is no. Yeah, you can see there is no phi. Okay, just come up with the relevant graph. Okay, so relevant figure. Okay, so that's why there is no phi. Yes, so you can substitute here and so Y value you can find out and substitute and find out the Ki we do tensile part and then bending component part. So in the bending component one, you need to find out the stress due to bending. So for that, you have idea about the sigma times my divided by I. So that equation you can substitute here with the bending moment. and find out the stress. That is stress. We are not going to apply in here the same stress with the tensile. This one you are not going to apply this one. This is stress. This is stress. We can't apply in here. You need to apply the due to bending moment stress. So you need to use sigma equals my divided by I at the surface, that A length. So you can calculate it. And Y value. So you need to get the relevant figure, and according to that you can get the Y value. And this equation also provided in the same figure, so you don't want to sometimes calculate it. So Y value you can easily find out using a W ratio, then substitute here, and you will get the Ki value due to bending. Get the summation of these two. So you will get the total K stress intensity factor. So you know what is the stress fracture toughness, critical stress intensity factor. It is 60. So it is this value is above 60. So you need to repair this one before use it. So that's all about the lectures part. So I will discuss with the tutorial this one. So until this point, do you have any questions? There is only two.
Professor,
Yeah.
so to get rid of this kind of the what's it called, the larger than the 60 through the fillet and the things, right?
I couldn't hear you properly. I don't know why. Can you repeat again?
The earlier problem, the Ki value is higher than the 60 now?
Yeah.
Yes. To get rid of the 62.5, we need to adjust the fillet and
You mean repair?
Yeah.
Okay. The repair part, you can fill the crack if you want, or you can machine it sometime. So you can remove the crack sometime, reduce the diameter, something like that. Are we clear?
Yes.
Or you can replace the bar sometime.
Okay.
Is it okay?
Okay, sir.
Okay. So refill means you need to weld it or something like that. Okay. You can't fill with some bind or something. Not enough. Should join together the two faces. The interface should be joined. Otherwise, effective cross-sectional area will be reduced. Okay. Okay. I will continue the tutorial one. I will explain this question only because there is only two questions, I think. Yes, two questions. Anyway, so in this question, so you can see the figure, there is a crack. Okay, so I will read it. The hook similar to that shown in figure 1 is part of
we can't.
Okay, I'm sorry, I didn't share it. Yeah, I will share it. Now can you see?
Yes, sir.
Okay. So this tutorial is I will read the question. Oh, similar to that shown in figure 1 is part of sacrificer. Use dig up all road near beds before replacing them. Let the tool be made of steel and heat treated properties indicated in table 1. Okay. As I told you, you can see in here, you need to find out the KIC with this graph table. Sorry, this table you need to find out KIC. The dimension of the tool are D values. D means this distance, and 2C is kind of width to diameter, and width of the rectangle. This is a rectangle, so Width of the rectangle cross-section is T 25 millimeter. Determine the magnitude of the fracture load P. Okay, this is the load P. So the crack length of A equals 5 millimeter and 10 millimeter. So you need to first consider A as 5 millimeter, then 10 millimeter. So you need to find out the crack length for the fracture load P. So you need to find the fracture load with the KIC, because A is provided. So you need to find the maximum P with the A when it's A 5 millimeter. KI value should be equal to KIC at that time P load. The same thing in here as well. So this is the arm what they are talking, this arm in here, and KIC value for the given material, it is 4340. 4340. Yeah, this one is 59 KIC. Okay, 59. So we know KIC value, and the conditions with this load, you can see this is the center axis of this shaft. Okay, if you know this part, if you consider this is as a two part, this one and this one, this is center axis. The crack is initiating here. So due to P load, this is under tension and bending. You can see if you transform these P loads here, it is under tension. At the same time, due to this distance, this one and this distance, okay, this is center axis. So center axis and this distance is C plus D. Due to that distance, there is a bending moment due to this P. So you need to find out the due to bending and tension K value, and K value with it should be equal to KIC. Then you can find out the P value with the given crack length. So that's the way we need to deal with this kind of questions. So it is the surface crack, so not the center crack. Yeah, this kind of crack. Okay. So you need to consider this diagram, case 4. Okay. So I can't rotate this one, but the case 4. So Ki value you can find out using this equation. So F lambda. So they mention here lambda. Okay, this ratio is lambda. So F lambda. So you can find out using this table, and due to bending, you can find out using this equation. Case 6. So you need to consider case 4 and case 6. Okay. So let's see how we can deal with these equations. From table 1, we know KIC 59 megapascal times square root meter at a sections through the crack. The hook is subjected to combined axial load, case 4 of table 2. I already can show you, and bending, case 6 of table 2. Since linear elastic analysis is assumed, LEFM, assume the state of stress for combined loading can be obtained by superposition of two states of stress for two type loading. Thus, yeah. So in here, don't worry about this one too much, because they calculate the sigma times F lambda. That means that Y value, sigma times Y value together. So this is superposition principle actually. Okay, so you can calculate separately and get the summation. This is kind of Ki. So when A equals 5 millimeter, lambda value you can calculate, because you know they provide the ratio is, you need to get as a lambda A divided by C. Sorry, I'm sorry. So let's see. In here, yes, I think it should be 2C. It should be C. Okay. So then just take it. Then from table 2, case 4 and 6, we obtain these values. Okay. So due to tensile load and due to bending load, the Y value, that F functions value, you can get from the equations given. This ratio not change, but with the table it can be changed. So you can find out the ratio. This is the table. So if you get the 0.1, what you need to do? Interpolate and find out the answer in between these two values for the f lambda. And if you get the same ratio, you will get from here. This crack is not changed. So if you get the 0.1, it has a in here. But if you get the 0.15, so you need to interpolate in these two values and get the required value for the f lambda like that. So, then you can find out the axial stress. So it is very easy because the axial stress is P upon A. So for sectional area, you can find out 2C times T. Then you can find out the stress, but stress with the P terms, because we are going to find out the maximum P value. So this is stress. The bending stress is, as I told you, sigma equals my time divided by I. So here m is P times D plus C. I already show you that distance. And C means this crack available at the surface. So we calculate the bending moment to this central axis. So distance to here C, center axis to this crack, distance C. So that is the C, and divide by this is second moment of inertia for the rectangular cross sections. So this is like a B and D, thickness and width. So relevant value you substitute and find out the bending stress. Okay. So it is also given by with the P. Okay. Then what you need to do, you need to find, you already find out the sigma, sigma value when the relevant f function. So you can multiply by that values and get the, because you don't want to consider about the too much about k, because the phi a part, just find out this value and it can be substituted here because this is KIC, it's a function of that part. So if you get the sum, so separately you can do whatever, it doesn't matter. So this is easy, but if you want to find out the KI by bending separately and KI due to tensile load, the separately you can calculate. In here what they did, so this K function has a sigma f lambda. So they calculate separately that part for the resultant thing and substitute here. That's all. So just get the summation of these two and substitute here. You can see phi a, we already know A is 5 millimeter. So it should be equal to 59 if it is a critical crack length. So that is the maximum load, then you can apply on there. So P maximum value is 23.7. So that's the way. 10 millimeter one. So what you need to do, you need to again calculate the ratio. That ratio will be changed. Then the function value also will be changed. Then bending moment stress and the axial tensile load will be not changed. That is, stress are not changed. Only changing F value. So you can find out again that resultant value, substitute here and find out the load value. So that's how we can find out the load value. So there is another questions, same questions. You need to redo the example with the condition D when it's 200 millimeter. Earlier it was a D value is D value was is a D value 100, as I remember 100. Sorry, 250. Now it is 200. It is less than earlier, and 2C it is 50. So dimensions is changed. You need to calculate the maximum P load for the crack length 5 millimeter and crack length 10 millimeter. So same way you can do the equations and you can calculate the things. And I think we already discussed this one. So this type of questions and the examples, you can deal with this question. So I think the values only change in here. So the thing is same. theory is same. So do you have any question you can ask? Otherwise, we can conclude this session. Any questions? Virant, Pramit, do you have any questions? Yeah.
So actually, so if we come across a question in the future, is there a way to contact you?
Yeah. So what you can do, I will arrange the next lecture. So after discuss the whole lecture next time, I can spend another 30 minutes or 45 minutes with you with your questions. No worries. I told you already that things.
Okay.
So not every day you can't contact me. So you don't do that. But you can keep the things you got with as a. So if you have any questions, if you can't understand some point when you study, so you can point out these things. So if you don't remember that, if you can't keep it in mind in these questions, you can note down that one. And when we discuss the things, you can ask that questions. So after finish the like this, okay. So after finish the lecture and tutorial, I will give the time for the discussion. So you can discuss whatever you want, and you need to show the thing what you need to ask, because so you can share your screen with me, and you can show this point I couldn't understand. So when I deal with these questions, I got this kind of confusion or something like that.
Okay.
So anything to ask about this? So actually this lecture series is finished now. So next week or next time we will discuss the buckling and Castiglione theorem, and then the thick wall cylinder. So that those are three different separate lessons. So that continuity is now we are going to break now. So until the lecture 7, there is a continuity. Whole lectures are linked together. And so today is the last lecture for that lecture series. So hope you understand there is only 2 parts. I don't know why. So if you have trouble at the exam, don't blame on me. And I will give another notice to you as well. So I will share this slide as well. So not slide, this window it. So can you see this?
Not yet, sir.
No.
Yes, sir. No.
Okay, you can see the course web, no? Can you see?
Yes.
Okay. So I want to give the one notice. I already emailed your batch trip and other one, the Praveen or someone, I don't know. So you can fill the feedback form. It's an online form, and there's a closing date 5th of July. So so I already shared the link and other things and how to do that. I think you already know how to do the give the feedback. But give the feedback. It will be helpful your junior batch, not only me. It will be helpful to your junior batch. Your feedback is very important. So I already passed the email, and I already put the notice on the course web, and I got some email from some of the students. They asked for the link to submit the course lab reports. So there is already links you can submit to your lab report, but Blackboard, I heard there is no link. So I contact Dr.
Yes,
Ian.
sir. Not yet.
Yeah, I contact already Dr. Ian. He didn't reply yet, but I already emailed him. So he will put, but or if you submit to the course web, we can inform you already submit on the date. I mean, on time you submit or something like that. And there is a one student, I think one of the students contact me yesterday. He submit the wrong link, report to wrong link in the backboard, here's what we can do. So
Yes, sir.
when you submit something, please careful, because this kind of matter is very primitive things. If we contact CERT-In, they will think that you guys are not responsible. Okay, so that's not good. So when you submit, you just
Sir,
yeah.
Sir, should we submit individually or?
No. It's a group work. So
Yeah.
even though
So
yeah,
one person in every group he can submit, no? So everybody doesn't have to submit, no?
no. That group is submit wrong link. That's a problem.
Okay.
So what I'm telling, so if I contact CERT-In and if I tell, so you this student submit to wrong link, and can you, so this is like a, you know what is a feeling like that, no? It's not good. So please be aware about that. I already informed to the relevant party, but if we already check it, and if that matter if it arise, we can contact, but don't, so just for a message I'm giving, so don't do that again. So it's not good. Okay. Yeah, please fill this feedback form, the evaluation form, and submit it as well. So that is the last notice I want to give you. And can I
Excuse
conclude?
me, sir.
Yeah.
The curve beam lab 2.
Yeah, they will not up. They already not mentioned the deadline, but they didn't upload the video. That I know the matter, but the deadline was 29th May, no. So they will upload the video later. Don't worry about. But sometimes you can prepare the lab report without the video. Some extent, no. You can't. You only can't do the calculation discussion, but other things you can do.
Yeah.
Okay. So my opinion is, what you can do the report preparations. Don't wait until their video, and if they provide the video data with the data as well, so you can do the calculation very quickly and do the discussion as well. So discussion also, some of the part without calculation you can do. Okay, so I mention it as in the stress consideration lab report also, because they mention you within 1 week, no, you need to submit that one. So you had some difficulties to submit. You had so many submissions or something like that. Rep told me. So then I asked from the doctor, and he told me you can give the deadline. No worries. I gave the deadline 11th May. So I hope you already submit that. But the thing is, lab 2 you don't have time for that. So if deadline I already fixed with the CERT-In one, but if we change it, your term is over. You know that.
Yeah.
So June 4th or 5th, your term is over. So you don't have much time to do the lab report. Then I mean submit to lab report later 29th. So please prepare your lab report and pass this message as well. And don't wait until their video. Prepare the report without calculation and discussion. Some extent you can do, but after upload that video, you can watch that and you can get the data and do the calculation and submit given time. That's the way.
Okay, sir. Okay, thanks.
Okay, thank you.